based on load impedance first type is shorted line. So for a shorted line, ZL must be equal to 0. Now if ZL is 0, then the input impedance of such line is called as ZSC, short circuited line, and this is nothing but Z of L, which we have already calculated for ZL equal to 0. So this is from impedance transformation relation, and we will get J into Z naught 10 Okay, before this, just let me modify the impedance transformation relation for lossless line so that we can get it easily. Okay, so before studying this shorted the lines based on load impedance, what we will do is we will modify the impedance transformation relation for a lossless line. Okay, so for a lossless line, what will happen? So impedance transformation relation, impedance transformation relation for lossless line. So why am I calculating for lossless line? Because here onwards in transmission line we will consider all the lines as lossless line. So for lossless line, Z of L is, so for lossless line we know that gamma is equal to J beta. So therefore this can be written as Z naught into ZL cos H J beta L. In place of gamma I have substituted J beta plus Z naught into sin H J beta L divided by Z naught into cos H J beta L plus ZL into sin H J beta L. So this can be written as, now cos J beta L is nothing but cos H J beta L is equal to cos beta L. This is from simple trigonometry, you can check it, and sin H J beta L is J sin beta L. So therefore Z of L will become, if I substitute this in this equation, I'll get Z naught into ZL cos beta L plus J sin beta L J into Z naught sin beta L divided by Z naught into cos beta L plus J ZL into sin beta L. If you take cos common, you will get Z naught into ZL plus J Z naught tan beta L divided by Z naught plus J ZL tan beta L, where beta L is called as electrical path length. So this is the this is very important now. This is nothing but the impedance transformation relation for a lossless transmission line. In many books you will find this as the input impedance also. They call it as input impedance. Yes, obviously you can find the impedance at any distance now. So if you take at the L, that is at the input at the source end, if you calculate the impedance, then this equation will give you obviously the input impedance of the transmission line. So in books, if you will find that this is also called as the input impedance of the transmission line. So this is very important relation. Now there are certain characteristics of this impedance transformation relation, and they are really very important. The first characteristics is characteristics of impedance transformation. So the first characteristics is that the impedance value repeats every lambda by 2 distance. So after every lambda by 2 distance, the impedance value will repeat. So you can check this with the help of the above equation. So if you find z of L plus lambda by 2, then you will again get z of L. So this is very important, that every lambda by 2 distance, after every lambda by 2 distance, the impedance value repeats. So here, if you observe the standing wave pattern, so the distance between two maximas or two minimas is nothing but lambda by 2. This is important. So between two maximas or between two minimas, the distance is lambda by 2. The second important point is, this is really very important, and this is that normalized impedance repeats every lambda by 4 distance. So after every lambda by 4 distance, the normalized impedance inverts. Sorry, do not repeat. Sorry, I'm extremely sorry. This is inverts. So after every lambda by 4 distance, the normalized impedance inverts. Now what does this means? What is normalized impedance? So normalized impedance is nothing but when you normalize the impedance with respect to the characteristic impedance. So if I consider load impedance and if I divide this with Z0, then this is called as ZL bar. This is the normalized load impedance. So any impedance which is divided by Z0 is called as the normalized impedance. Now here what he is saying is that the normalized impedance Z bar, it is always the normalized impedance are denoted by a symbol bar. We place a bar on the impedance. So Z bar of L plus lambda by 4 is 1 by Z bar of L. It is 1 by Z bar of L. So after every lambda by 4 distance, the normalized impedance inverts. So these 2 points are really very important. And third point is that if ZL is equal to Z0, if my load impedance is characteristic impedance, then that line is called a matched impedance, matched case. This is very important, because in this case what will happen, if ZL equal to Z0, then this Z of L will be equal to Z0. It will be independent of the distance now. Till now we have seen that the impedance completely depends on the distance of from the load end, that is the value of L. But here what we are observing here, that when ZL equal to Z0, the line will the impedance at any point on the transmission line will be Z0, and this is called as the matched case. Now why this is happening? Because if this is my transmission line whose characteristic impedance is Z0, and if my load impedance is also Z0, then from we know that maximum power transfer theorem, we have studied maximum power transfer theorem. So according to maximum power transfer theorem, if the load impedance is equal to the source impedance, in that case maximum power transfer occurs. And for this case, in this case the impedances are matched, and therefore this is called as matched case, and in this case the maximum power will get transferred in the transmission line. Okay. So these three properties are really very important, and they play a vital role in the study of Smith chart also. We'll see them again in Smith chart. Just for the time being, they are very important and you need to know them. Okay. Now we were studying the types of transmission line based on load impedance. Now that is also very important. So the classification of transmission line, based on load impedance. First type is short circuited line. So for short circuited line, ZL is 0, that is load impedance is 0. Now in this case, we denote the impedance as ZSC, input impedance as ZSC. So this is Z of L with ZL equal to 0. So if you substitute this in the impedance transformation relation, you will get J Z naught tan beta L. So this is important now. We got J Z naught tan beta L. Now, if I calculate the load reflection coefficient ZL, tau L. So tau L is ZL minus Z naught divided by ZL plus Z naught. So this comes out to be since ZL equal to 0, this is minus 1. Now, if I plot this impedance, it will be like this. This is beta L, the electrical path length. So if I plot ZSC versus beta L, I'll get like this. This is pi by 2, this is pi, this is 3 pi by 2, and this is 2 pi. This is, so beta L equal to pi by 2. This means L is equal to lambda by 4, because beta is 2 pi by lambda into L is lambda by 4. So this lambda gets cancelled. So this is pi by 2. So this is L is lambda by 4. This is L equal to lambda by 2. In this way. So what do we observe here is that we can use a short circuited line as circuit elements. So if the length of the transmission line, if the length of a short circuited transmission line is chosen such that it is between 0 to L is equal to lambda by 4, then that particular transmission line can be used as an inductor because its input impedance is inductive. So therefore we can use the short circuited transmission line as a inductor or a capacitor based on its length. The second type of transmission line is the open circuited line. Open circuited line and for this ZL is infinity. Now we will call this the impedance as ZOC. So ZOC is limit ZL tends to infinity Z of L, and this comes out to be Z0 by J tan beta L. Just substitute this in the impedance transformation relation. We will get minus J Z0 cot beta L. Again for this, tau L is 1. The load reflection coefficient is 1. That means maximum full reflection. Tau L equal to 1 means full reflection. That is, the wave will not be absorbed, it will be completely reflected back. If I plot this, so this is my ZOC versus beta L. This is inductive and this is capacitive. This is pi by 2 pi 3 pi by 2 and 2 pi. So this is for both open circuited line as well as short circuited line, the input impedance is reactive, and based on its length you can use it either as an inductor or a capacitor. This is very important application of transmission line. Also, if you multiply ZSC and ZOC, you will get the Z0 square. This is also important, and many times a question is being asked on this particular relation. So this relation is really very important. So this particular topic, the lossless transmission line, is very important from exam point of view, as well as this short circuited line and open circuited line. The question is being frequently asked on these two topics. So please pay special attention to these topics. Next we will study the voltage standing wave ratio, VSWR. Again, one more very important point, very important topic, the voltage. Okay, let me write it as VSWR. VSWR, voltage standing wave ratio. So voltage standing wave ratio is denoted by this rho, and this is Vmax divided by Vmin. Now, what is the maximum voltage on a transmission line? So the maximum voltage on a transmission line is okay. I have to find the values of Vmax and Vmin. So I'm just giving you the values for the time here. We need not go into the derivations now. So Vmax is V plus into 1 plus mod of tau L. This is the maximum voltage on a transmission line, because we have seen that the energy is transferring, energy is being transferred in the form of voltages and currents on a transmission line. So the maximum voltage which is possible on a transmission line is this, whereas minimum voltage which is possible is V plus into 1 minus mod of tau L. This is minimum voltage. So therefore the value of voltage VSWR is 1 plus mod of tau L divided by 1 minus mod of tau L. Similarly, we can define one more term which is called as ISWR, that is current standing wave ratio. Okay, that is not required actually. Actually, it is voltage. We have defined reflection coefficient as forward traveling wave and backward traveling wave. So earlier, whatever we defined was the voltage reflection coefficient. Similarly, current reflection coefficient is possible. So this is VSWR. This is very important. Now, there was a question in GATE that if the uh, what can be the minimum and maximum value of a VSWR. So we know that for no reflection case, the reflection coefficient is 0. So when reflection coefficient is 0, the VSWR will be 1. So the minimum value of reflection coefficient is 1, whereas the maximum value is infinity. When tau L is 1, it will be infinity. So the reflection, so the VSWR, it can vary between 1 and infinity. So for no reflection case, it is 1. So 1 means no reflection and infinity means full reflection. Full reflection. So we have seen maximum impedance, maximum voltage. Now we will find the value of maximum and minimum impedance on transmission line. So maximum and minimum impedance on transmission line. Fine. So we have seen that Vmax value is known to me, and similarly the value of Imax, the maximum current, is, so we have written the value of Imax and Imin. So Vmax and Vmin, Imax is V plus divided by Z naught into 1 plus mod of tau L which is Vmax divided by Z naught, and Imin is Vmin divided by Z naught. Now when the when the impedance, the resistance will be maximum, since we are considering the lossless transmission line, therefore I am calling it as resistance. So what is, okay, let me consider impedance only. Okay, so what is the value of Z max, the impedance, maximum impedance on transmission line, when the voltage will be maximum and the current will be minimum. If the voltage is maximum and current is minimum, then in that particular case it is called as, in that particular case the impedance will be maximum. Now what is I mean? I mean is V min divided by Z naught. We have already seen this. So this is V max divided by V min divided by Z naught. What is V max by V min? This is nothing but VSWR. So rho into Z naught. And for a lossless transmission line, Z naught is purely resistive. So hence this can also be written as R max, maximum resistance. So the maximum impedance will be purely resistive. Similarly, Z min will be Z naught divided by rho. Just check it. When will be the impedance minimum? When voltage is minimum and current will be maximum. In that case, you will have minimum impedance. So these are two important relations. So this is all about the theory of transmission line. Now we have finished the one part of transmission line and we are left with the another part, that is Smith chart. So before that we will solve a few problems based on transmission line. So let me consider this problem. An airline has Z0 equal to 70 ohm and beta is equal to 3 radian per meter at 100 megahertz. Calculate and capacitance of the line. Now, since the given line is airline, so airline is lossless. Airline is lossless. Since its conductivity is 0. Now, for a lossless line, we know that R equal to G equal to 0, and we also know that its attenuation is 0. Now Z0 is given and beta is given to me. For a lossless line, we know that beta is omega into under root LC. Since frequency is given, I can calculate the value of omega. So this is equation number 1. So in this equation, omega and beta are known to me. Similarly, Z0 is under root L by C. This is also known to me. This is second equation. Now if you solve these two equations, you will get the value of L and C. So L comes out to be 334.2 nanohenry per meter, whereas C is 68.2 picofarad per meter. There is one more problem. For a given that the line is distortionless line, so distortionless line is distortionless line. Z0 is given as 60 ohm, alpha is 20 millineper per meter, velocity is 0.6 c. We have to find the value of find R, L, G, C and lambda at 100 megahertz. Now, since the line is distortionless, for distortionless transmission line, we know that again Z0 is under root L by C, and also alpha is equal to under root RG, and V is equal to 1 by under root LC. Now, from this, we know that R by L equal to G by C. For a distortionless transmission line, R by L equal to G by C. So what can I do is, I'll replace G with RC by L. So here in the alpha I can write this as under root of R into G can be written as R into C by L. So this comes out to be R into under root C by L. we know that L by C is nothing but Z naught, under root L by C. So what about under root C by L? So under root C by L is, it's R by Z naught. So from this expression I can get the value of R. R is alpha into Z naught. So therefore R will be 1.2 ohm per meter. So in this way we have got the value of R. Next, we can easily get the value of L. We can easily get the value of L now. So what is the value of L? So L is equal to Z naught divided by V. Just slight modification in the velocity equation. So this will be 333 nanohenry per meter. Now we have alpha is equal to under root Rg. R and alpha are known to me. So I can get the value of G. So G will be alpha square divided by R, which comes out to be 333 microsecond per meter. Microsiemen per meter, sorry. And finally, V into Z naught is 1 by C. If you multiply the velocity equation and Z naught, I'll get 1 by C. So this implies C is equal to 1 by V into Z naught. So if you multiply this, you will get 92.59 picofarad per meter. Also lambda is required. So lambda is C by F. C and F are known to me now. Sorry, V by F, velocity by frequency. V and F are known to me. So this is 1.8 meter. So in this way you can solve the problems of distortionless transmission line and the lossless line. Now there are problems based on the formulas of VSWR and reflection coefficient. So I request the students to please be very careful with those formulas. There are few conceptual questions also. Okay. So if the yes, on the length of transmission line for short circuited line and the open circuited line, based on length the questions may come. So for a short circuited line, if the length is less than lambda by 4, then how can you use this transmission line? What will be the behavior of this transmission line? So for L less than lambda by 4, its impedance ZSC is J Z naught tan beta L. This will be positive. So this will be inductive. So you can use this as an inductor. So for L less than lambda by 4, a short circuited transmission line can be used as an inductor. For lambda by 4 less than L less than lambda by 2, you can use this transmission line as, so ZSC will be in this case minus JZ naught. So it will be negative actually. So ZSC will be capacitive, and therefore you can use this as a capacitor. Then for L equal to lambda by 4, the impedance is infinity. ZSC is infinity. And for L equal to lambda by 2, ZSC is 0.